Hello students, Miss Slyman here. We're going to be thinking about some related rates. And often we think about balloons with related rates because it's super easy to visualize. So if I have a balloon, then if I'm going to fill up this balloon, I'm going to attach my hose and put some air in. So it'll go into the balloon, and as that happens, then my balloon is going to get bigger. So as the volume goes in, the radius of my balloon changes. So here's my radius. Put that in there. And we can think about as we add more and more air, the balloon gets bigger, the radius gets bigger. So the equation that relates the radius of the balloon to the quantity of air, well, quantity of air is volume. And I know because I have it memorized, maybe you need to look it up, but the volume of a sphere is 4/3 pi r cubed. In your printout, I'm not sure, I think it printed too soon, so your table values are missing. So go ahead and fill in these table values. So we're assuming that we've been told some data here that after 1 second, the volume of the balloon is 2 cubic feet. After 2 seconds, it's 4 cubic feet, et cetera, et cetera. So I could use this equation to help me find the radius. So rearranging this equation, this implies that my radius cubed is going to be 3 times the volume over 4 pi. So that means that the radius, I'm going to take the cube root of both sides. And if we have feet cubed, our radius, of course, is going to be in feet. And so I can use this to find my radius. So after 1 second, I'm going to come in here. Let me clear out my history. Okay, so we had 2 cubic feet. So I'm going to do the cube root of, so I've got the cube root, and then I'm going to go into there. I'm going to put in a fraction. All right, we had 3 times the volume over 4 pi. So I'm going to say 3, actually, I'm going to clear all of this out and use my calculator more effectively. So the first thing I'm going to do is store 2. So I'm going to take that, I'm going to take 2, I'm going to store it as the letter A. My variable is in use. Interesting. Okay, I'm going to take 2 and I'm going to store it as V. All right, so now I'm going to put in my equation for the radius, which was the cube root of 3 times the volume. Pick my letter over 4 times pi. Let me just make sure I'm doing the right thing. 3 volume over 4 pi. And then I'm going to go ahead and hit Control Enter to get an approximation. I get 0.78. And now I can just I can modify my volume to match my different values and just recalculate my radius values. So 0.78, and again, always at least 3 decimals. So 0.7816, I'm going to say, for when the volume was 4, 9847. When the volume is 6. The other thing I can do is go into this, take out my V, put in my 6. Maybe that's even easier. Control Enter. Not what I wanted. Make sure I go to the outside. Control Enter. All right. Go into the inside, make that an 8, come out to the outside. Again. Control Enter. Okay, so we have, let's see here, 1127, 12407, 1.2407, and last one, let's go up and do that and Control Enter. Ah, goodness gracious. Love it. Why? Why? I don't understand why it's not giving me the decimal approximation. 1.3365. Hopefully you did that faster than me. Okay, so now we want to know what rate the volume is changing. Well, I can see that every second the volume is increasing by 2 cubic feet. So I can say 2 feet cubed per second. Now, is the radius changing at a constant rate? Well, I can find the difference between all of these. This one looks to be about 0.2. Over here, it's not quite 0.2 because that would put me up at 1.18. Definitely not 0.2 here because now I'm going up by about 0.12. So no, the difference isn't the same. And that makes sense because as we add more air to this balloon, even though the volume of air going in, that rate is staying the same, the balloon grows quickly at the beginning, but then as it gets bigger, there's more space for air to be in, so it doesn't stretch it as much. So let's think about how we could find the rate at which the radius is changing. And this is why we call it related rates, because we're comparing two rates to each other. So the volume of the balloon depends on how much time has passed. We can rewrite our volume in terms of the radius changing as a function of t. So now my independent variable, well, independent variable is always time. An equation for how the volume is changing with respect to time, I know that that's constant. dv dt is just a constant 2. At the instant when the radius is 1.5 feet, how fast is it changing? Well, I need to find a formula. I want to find dr dt. So that's what I'm looking for. I know that volume was 4/3. Let's make that actually 4/3. Pi r cubed. I want to find the derivative of this with respect to t. So dv dt is what I have on my left side. My right-hand side is going to be chain rule. So derivative of r with respect to time, that's my inside, that's my dr dt, which I don't know. And then derivative of the outside, 3 times 4/3 is 4, pi r squared. Well, I know dv dt. That was something I had earlier, so I can plug that in. 2 equals dr dt times 4 pi r squared. Now I know that the radius is 1.5 feet, so I'm going to plug in 1.5 feet, and I'm going to find my expression for dr dt. So 2 divided by 4 times pi times 1.5 squared is going to be equal to my instantaneous rate of change of the radius. Let's go ahead and put that in our calculator. So 2 divided by 4 times pi times 1.5 squared, and we get 0.0707. That's going to be feet per second. So is the radius growing faster when the radius is smaller when it's large? Well, we saw that already and we thought about that already. that it's growing faster when the radius is small, I can also see that in this equation. So my equation for dr dt was equal to 2 divided by 4 pi r squared. Well, as r gets bigger, I'm going to have 2 divided by a bigger and bigger number, which means it's going to decrease. So this is going to be bigger when the radius is smaller. So it grows faster when the radius is smaller. All right. I'm sure you'll have questions about this, and I can't wait to talk to you about it in class.